are the kind of things that I've gave to try and compensate if you're short of time, or if you feel that there's something you need. And totally feel free to shoot an email me, and I'll try and answer either directly by email or Zoom meeting if that's not really practical. So that's kind of where we are as far as resources I've got. Now you notice that every single chapter has its own individual small videos on various topics. So if you want to get another insight or another way of looking at something, that's another resource for you. Are we good? Right. Okay. Now, I think we're about to start chapter 3. We may already have got my brain. I can never remember which thing we have covered. Did we look at measures of center at all? Perfect. So we're starting from scratch then. What you're going to have to do very often in mathematics is that you collect your data, right? So we've done that. And that, you know, it could be a simple random sample, but you've got some good data. And then the second thing that you do is you summarize it in some way. And that basically means you do some type of graphical thing. So that would be histograms and bar charts and time series and stem and leaves and group frequency tables and all that thing. Now we're going to look at how do you summarize the data numerically. There are two main things that we do. We find what's called the measure of center. I think I got someone who needs to join the class. If you could wait a second, how am I going to do that? Oh, they disappeared. Right, measure of center is basically a number. In statistics, a number that tells you something about the population, something. Let's see if I can catch it this time. Tells you something about the sample or the population. It's called a statistic. So there's a statistic out there. That's where the name statistics comes from. And it's a single number, one number, that tells you something about the sample or the population. There are two main groups to that. One measures the center. There are three versions of that. Mean, mode, and median. They are all collectively called averages. We typically use the term average very loosely. Normally when we say average, we mean the mean. That's where you add up all the numbers and you divide by how many. But there are three kinds of averages. The mean is the one that most people know about. You add all the numbers, right? And then you divide by how many there are. The mode is the most popular answer. And then the median is the middle number. So we're going to look first today at this statistic, which is the measure of center. It basically, you were going to find one number. It's a bit long, there we go. We have one number that essentially tells us give me a number that's like the typical person in that group, right? Not the biggest, not the smallest, but somebody kind of sort of in the middle. That's really what we're looking for. So that's why it's called a measure of the center, right? Measure of the center. Let's do some data and show you how to do all three. Let's suppose I have some data 1, 3, 4, 5, 7, 7, 9, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have a sample of just 10 people, right? 10 ages, 10 numbers, right? Let's see how that works. If you want to get the mean, you add them all up. So that's 4, 8, 13, 20, 27, 36, 47, 57, 61. That's 91. You divide it by 10 and you get the answer 9.1. I'm sure, I can't think of anybody who's never done that. Are you all comfortable? You probably called that the average when you did it, but its real name is the mean. You're all happy with that thing? It's just add a whole load of numbers and divide by how many there are, and we are good. Now the mode is, if you scan through that data, do you notice that there are two number 7s? In fact, although it's not that popular, isn't the number 7 more popular than any other data, right? So if you had a list of data and there were 8 number 4s, and that was the most popular, then the mode would be 8. So it's not how many times it happens, it's the number itself, right? In this case, the number 7 is the most popular, so we call that mode. And then we have the third one, which is called the median. Now, the middle number, let's see what that looks like. If you look at 10 numbers, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You get those 5, and then you get those 5. Do you see in this case, there are a shared pair of numbers in the middle, right? There's 2 numbers in the middle, right? Aren't both those 7s equally in the middle? So in this case, the median is 7. So if I was talking about this set of data and I was saying, what's the typical value of this data? The median, we'd say it's about 7, right? It's roughly the number in the middle. And the mode in this case just happens to be luck, but it happens also to be 7. And the mean happens to be a little bit bigger than the other two. It's about 9.1. We cool with that? Any questions? Now, when you're calculating the guy called the mean, if the information that you're using, the data that you're using is the entire population, then it uses this letter of the alphabet and it's pronounced mu. It's a Greek letter mu. So if someone says, I've got some amount of data and it's mu equals 70, you can say, oh, you asked every single person in the population and the mean ended up being 70. So that Greek letter is actually telling you a lot. If, however, you only use a sample of people, right? I only asked 100 people in the population, then the mean is called that funny little X with a line on top of it. I don't know if you've ever seen that notation. And that is equal to, or that we call X bar. So you imagine you only got 100 numbers in your sample and you added them all up and divided by 100, you would call it X bar. If you asked every single person in the population, you would call it mu. We good? Now, let's look at some practical issues about calculating these things. Right, that's me rewritten the entire data set again. Except I'm going to do one more thing. I'm going to add one extra data point. Just by looking at it, isn't 120 an outlier? It's an exceptionally big number, especially when you compare it to the rest of the data. Let's find out what does an outlier do to the averages. So this is the mean before the outlier came, this is the mode before the outlier came, and this is the median before the outlier came. Let's see what happens now. Well, if you add up all 11 numbers, you will get 211. And you divide by the 11 numbers, and the mean has now grown to 19.2. Do you see that that one outlier has doubled the value of the mean? Just one number has caused a huge difference in the mean. Would you also agree, I hope you agree anyway, would you agree that 19.2 is not the typical kind of value that this data has got? I mean, it's been wasted, if you like, for a better word. It's been wasted by that 120, because 19.2 is almost here, and you see that's nowhere near the middle. Isn't kind of sort of a here the middle? You know, we'd be looking for numbers in this range where my finger is moving up and down. So that one gets changed. Is the mode still 7? Yeah. So does the mode get affected by an outlier? No. Does the mean get affected by an outlier? Yep. Big outliers make the mean a lot bigger. Small outliers can make in a different set of data. Small outliers can make the mean much smaller than it should be. And the last one on the list, I wonder what happens to the median. Right, there are 11 numbers now. 1, 2, 3, 4, 5. Ah, do you see in this case there's only one number in the middle? And it's 7. So what is the effect of an outlier? Typically, outliers only affect the mean in any substantial way. I have a nickname for this. I call that the Bill Gates effect. So the story goes something like this. Imagine that I found out what the average wealth of everybody in this class, our class is, right? And it came out at $20,000, right? That was the average. And then Bill Gates just joined our class. Do you know what the average wealth of our class would be? We'd all be millionaires. We didn't all suddenly become rich. Didn't Bill Gates 20 billion or whatever the guy's worth, when you average it amongst us, caused a lot of damage to the mean. It made the mean unrealistic anymore, right? That's what outliers can do for you. They are bad things for the mean. It wouldn't really have affected our outlier. The outlier would not have affected the median. See, if we got everybody in the class and we put you in the poor person who had the least amount of money and Bill Gates at the other end, and then I walked along and I said, okay, you're in the middle of the group. How much money are you worth? Can you imagine that one extra number at the end, Bill Gates, doesn't have any effect on the median, any significant effect? So when the government takes data and they issue any kind of summary of the typical person in America or in Washington State for that matter, they almost always use the median when they talk about that. So the next time you might hear some data, well, listen carefully and you'll hear this. They'll say the median age of Americans is 32. The median house value is 220,000. The median salary is 52,000. You know, things like this. They always use the word median. And the reason they do that is because of the Bill Gates effect. Can you imagine if you put Bill Gates into Washington? Wouldn't it like double everybody's salary? It would be an unrealistic representation of the center, right? The typical whatever it is you're measuring. So we have to be aware of that. How do you think you physically cope with data if you look at it and you realize there is a sore thumb sticking out outlier like there is here, and you still wanted to use the mean? What would be the approach, do you think, to solving that issue?
Would you just pitch the outlier?
Yeah, just ditch it. And essentially say the mean was 9.1. And then just to keep everything legal, you might put down as a little note. Imagine this was some kind of paper that you were writing. One outlier of 120 was removed from the analysis. So people know that you weren't trying to hide anything, but you were doing it for valid reasons. And people who understand how to read information would say, yeah, I understand why you took that out when you were calculating the mean, because it was more realistic without it than it would have been if you used it. And that's essentially how you do it. Here's another different set of data. And we may disagree with the book, and that's fine. I don't mind disagreeing with people. In this set of data, which number or numbers are the most popular? Because that's the mode. It's not meant to be a trick question. What numbers are the most popular in this data set?
Both 3 and 5.
Yeah. Would you agree that there's quite a lot of 3s and the same number of 5s? It's like a draw, a popularity contest. The number 3 and the number 5 drew, right? The vote was the same, 3 votes for each. Now, here is the 2 different ways in which people in statistics deal with it. There are 2 quite different approaches to that answer. One of them says that you say that the mode, or I guess you have to pluralize it now, the modes are 3 and 5. And there's another group of people, in which I'm one of them, and they say there's none. So let me argue, not just me personally, because there's lots of people who agree with me. Probably more people agree with me than agree with this version. The reason I'm saying none is, let's be lawyer-esque about it for a minute. Shouldn't a statistic be a single number that tells you something about the center of the data, right? One number. That's 2 numbers, isn't it? It's not 1 number. So I'm kicking it out under that, you broke the rules, right? That's the first reason. Second reason is, can you imagine that you had a whole load of data and there was only 1 number of each, right? 1 number 5, 1 number 6, 1 number 22, 1 number 23. Does that mean, according to this way of doing it, does that mean that you write down every single number as the mode? Because there's 1 of them? You see, that's a bit silly, isn't it? In fact, see the people who do this version, they even have a rule that you're not allowed to have more than 2 or 3. If you have more than 2 and 3, they say none as well. So it's just about how many do you need modes before you decide there isn't a single mode anymore, right? And so we're going to go by the rule that if there's 2 The answer is none. I believe the homework is good. At least the ones I recognise, they only made it so one guy won. There was always just one answer and you didn't need to worry about it, right? So you had a set of data and there was more sevens than anybody else. You wrote 7. There's no argument. But that little fine point, I think, is worth talking about. Now here's another thing I want to talk about in the comparison of the mean and the median, because they can actually tell you some other things. So here we go. We're only going to look here at the mean and the median and what the data might be able to tell us about the basic shape you remember we talked about the shapes of a unimodal distribution, and there was 3 versions of it. There was a single hill. There was a single hill with a little tail to the right. There was a single hill and a little tail to the left. Remember those guys? This fella here is called symmetric. This here is called skewed to the right. And this guy here is called skewed to the left. Can anyone remember the shortcut for how to remember that this is called skewed right and this one is called skewed left? Because it's easy to mix the 2 names up, isn't it?
I just look at which way the tail's going.
That's how I do it. The little skinny bit is like the tail. Think of that as the head. Actually, I think that's a name that they use in some textbooks. This is the head of the data and this is the tail. And see the little doggy tail this way? Right hand tail. See the doggy's tail over here? Left hand tail. Right hand tail, skew to the right. Left hand tail, skew to the left. Now, I'll put it over here. Suppose that the mean was 51, right? And that the mode was, say, 50. It's not unusual that you get data where these 2 numbers are very similar or identical. In this case, they're very similar. When that happens, you typically get, oops, dogs are paying us a visit. Come on, guys, let's go. Come on, Maggie. Come on, Billy. Billy, come on. There you go. Sorry about that. Right, where were we? So if you have the mean and the mode and they're basically the same, you don't need to be exactly 50, right? But one's 49, the other's 50, one's 48, the other's 50, that kind of, close enough, then you're pretty much going to be looking at symmetric data. And not only that is, do you see the top of the hill? It's going to be somewhere in that range, the 50-51 range. So even although you don't know any of the numbers, if I only told you this, that I had some unimodal data and the mean was 51 and the mode was 50, it would be considered a pretty intelligent conclusion that you're probably looking at data distribution that looks like this. Now, suppose the mean was 51. Oh, let's choose 2 different numbers. So yeah, suppose the mean was 110 and the mode was 80. Right? Significantly different now, right? That generates one of these 2 typically. So if you had unimodal data whose mean was 110, but whose mode was the number 80, you'd have one of these shapes. Anybody want to have a guess at it, or even maybe think it through? Which shape do you think you get?
Wouldn't it be skewed to the right?
Yes.
Because the mean, I would think the mean would be pulled towards the outliers on the tail end.
You nailed it. You probably said it better than I was going to say it. Yeah. In case someone didn't kind of hear it, do you want to say that last sentence again about the pull to the right kind of thing?
Yeah, well, I mean, because in a basic parabola, the mean and median will be right in the middle, but as it gets skewed, you're going to have outliers that are going to be pulling that mean either up or down. So if the mean is higher than the mode, especially because the mode is going to be where the hump is, then that's going to be the mean is going to be the direction that it's skewed.
Yeah, good. I liked your first sentence better. It was cleaner,
Yeah.
right? But you know, that's what your brain does. The first time round, it says it quite cleanly, and then you kind of overanalyze it a little bit too much the second time. Yeah. You see, the mode tends to be where the hill is, right? Typically. And can you see that in this case, the tail is dragging the mean? The tail tends to be the feature that's dragging the mean to it. So you can imagine what the third one's going to be, but for completeness, I should put it in, right? Suppose then, so in this case here, that number there would be 80, and this one would be about 110. Do you see it's getting pulled to the right? In this last example, maybe the mean is 30, and the mode say is 60. In this case, then, the mean would be, you know, wherever the tail is, the mean tends to get pulled towards that, maybe make the tail a bit longer so it's more realistic. That would probably be about 30, and roughly where the hill is, and that's where the mode is, and that would be 60. So if you were given very limited information, if I basically said, you've got some data that's unimodal, and the mean is 30, and the mode is 60, what kind of shape would you expect the data to be? You would say skewed left. If I gave you this information, you'd say skewed right. If I gave you this kind of information, you'd say symmetric. So just only knowing those two numbers, you see you get quite a lot of insight into what 200 data sets might be. Looking good? Move on. Right. Next thing I want to show you is a cool trick. Suppose I want to find the mean and the median of a whole set of data. Right. That set of data there. That's maybe number 5. Now, some of the homework questions, you get a data set that's roughly 4 rows, right? So there's like 20 numbers in it, or some ridiculous 24 numbers. If the data is in order, it's a little bit easier, but not very easy, because if you want to find the median, don't you have to imagine them as one big long line, and then you kind of work along and you say, you're in the middle, so the mode, the median is that guy. Or there's 2 guys in the middle, so it's kind of the average of the 2. And that's a lot of work. If you want to get the mean, it doesn't matter if they're all jumbled up. Can't you just add them all up and divide by how many there are? But even that's quite a lot of work, because you have to remember to hit adds. And not that I've ever made a mistake in my life, but I can imagine other people who, if you were doing this by hand, isn't it easy to miss a digit, miss a number when you're putting them in order? Or when you're hitting the buttons on your calculator to type 25 when you meant to type 52. And it's just fraught with danger. And wouldn't it be nice, and this is where the trick's coming in, if there was a way in which we could get those things done on our calculator? Right, now if you have a TI-84, which I hope you do, you should be able to do what I'm about to do physically on your calculator. And if you don't have a TI-84, there is a link, and I'm looking to see if I've got it here. Right, I will put that link on. This little program here is called WABA-EMU. One of my other students has got a TI-84 emulator that you can use on her Apple phone. So she's promised to send me a link to that. When I get that, I'll put it on Canvas. It's free. Basically, it's just, it allows your phone to pretend that it's a TI-84, which is kind of cool. And if you've physically got one, which is kind of the best solution, right? That's the best way to do it, right? But I mean, this is an alternate. If you want to, and you want a physical one, because that's the best way for your, to handle, they have one that's got real buttons that you can press. Contact the Mesh office, MESH. You'll probably get to speak to Cheryl. And we have calculators that we'll give you a loaner for, some TI-84s. And she'll figure out some kind of non-social distancing way to get you them. Right. So I promised that the calculator was going to find all these good stuff. First, are you looking at that calculator? Okay, so there we go. You're still looking at it. Right.
Yeah.
You hit the little button and you put on, because it's actually that good an emulator, you have to pretend you're switching it on. Right, that's how good it is. Now, first thing you're going to have to do is to put all those numbers I wrote down in a piece of paper. So you hit the start button. So if you've got your own calculator and you want to kind of do this with me, feel free. If not, you can go back and look at this piece of the video and just go through the steps. Now, when you hit that, do you see there's a whole load of things, but number 1, edit is the guy you want, and you hit enter. And then you just type in your numbers. So here goes. I have 1, 3, 5, 63, 27, 45, 15, 23, 71, 61. Now I'm going to do a deliberate mistake here. There's only 161, but let's say that my dog came in and I end up hitting 61 again because I forgot I'd already done it, right? So that's a mistake, and I'll show you in a moment how we can fix that. And there's 21, and then there's finally 25. So you put your data in, and then I go, oh God, I put in too many 61s. Does that mean I have to start all over again and I'll clear it out and go back? No. If there's a number that shouldn't be there, you move the little cursor to where it is, and then you hit DEL, which is short for delete. Now it's gone. So if you notice that you've doubled up on a number, easy to fix. Another mistake I could have made is, oh, there's another number at the end, I just missed it. There's a 22 I forgot to type in. So just type it in at the end, because it doesn't matter which order it's in. Just type it in. Now, that's the data in. That's like step 1, get the data in. Now, we're going to get the calculator, as I promised, to find the mean and to find the median, right? So let's see what that looks like. Once your data is in, you hit Start button. And you notice this second one here called Calc. You move over to Calc. And you see it's on number 1 for 1 variable stats. That's exactly what we want. And I hit enter. And it depends. This is an older emulator. If you've got a newer TI-84, this window is a little bit different. In fact, it's a little bit easier because this window already has L1 in it. I need to tell the calculator where the numbers are. If you remember the data, it was in columns, and the column we used was L1. So I have to get L1 here. Do you see the one right above it? There's a little blue L1. So blue button, 1, L1. And I hit enter. And here's all the good stuff. In fact, not only all the good stuff, a whole load of other good stuff that I don't need right now. Do you see that little X bar? The mean. And in this case, 29.4, because I'll round it off. There are 13 numbers there. Some stuff that we won't worry about until the next section. And if I scroll far enough, do you see MED, median? Is 23. So do you see it found the middle number, the median, 23. It found the mean, 29.4. And do you see how much more accurate it is, and there's less chance of me screwing up because the calculator's, you know, doing all the heavy lifting for me? That's a godsend, trust me. Can you imagine some of the questions you're going to have to do 40 numbers? Okay, it takes you a few minutes, maybe a couple of minutes at most, right, to type in 40 numbers. But isn't that the hard part over then? Right, a couple of more buttons and you're finished. So here is my summary of that data that I just typed in. Right. So here is the data. The mean is 29.4, the median is 23. Based on only that data, do you think we're going to be skewed right, skewed left, or symmetric? And you have to commit to one of the three. Skewed right, skewed left, or symmetric. You're frightened to be wrong, aren't you? It's okay to be wrong. Because in a lot of ways, you learn more from your mistakes than you ever learn from the things you get right. Would you agree that the mean is bigger than the median? It's that, you know, that question, how long is a piece of string? What they're getting at there is that very often a lot of decisions are quite subjective, right? You look at something, you say, I think it's 12 inches. Somebody looks at a piece of string and thinks it's 10. Nobody really knows who's right unless you get a ruler out, right? And, you know, or tape, measure it, right? There's a lot of subjectiveness. In this case here, this is, in my opinion, bigger than that. Not just a little bit, but noticeably bigger. And because this is bigger, what kind of skewedness should you get?
Be skewed to the right.
The way I look at it is, if the mean is bigger than the median, you're skewed to the right. If the mean is less than the median, you're skewed to the left. If the mean and the median are pretty much the same number, you're going to get symmetric. But pretty much the same number isn't 23 and 29. Pretty much the same number is like 23 and 25, right? Or 23 and 21, right? A couple of numbers out, but not 6 out, right? Not 25% out. That's too much out. That's why I'm committed to this version. So although I have a small set of data, I could make the assumption that the population probably will look very similar to skewed to the right. So I would be expecting, if you collected the data on everybody in the population, the data would have a kind of shape like that, right? A little bit more rightness than there is leftness. I would also make a prediction that round about there is 23, and you know, the mean is a little bit further on, it's over here somewhere. And only for this small sample, I can make some conjectures. They're not always right, but there's a good chance that they are. That the entire population is probably slightly skewed to the right, and that roughly, very roughly, about somewhere in the region 23-ish is probably going to be the typical person in that centre. Are we good? Right. Let's look at another way, or why you would want to use means and medians. Typically, modes are pretty useless except when you're doing ordinal or nominal data, in which case it could make sense to say the mode is red, right? More people like red than any other color, right? So that would be a useful use of it. Do you know that trying to calculate the median or the mean of colors is pointless? I'll give you a very simple data set. Blue, red, and green. So you asked a big bunch of kids, what's your favorite color? And 14 of them said red. So in this world, the mode is red. It's not the 14, it's the thing that they liked. It's the red, right? That does make sense, agreed? Is there any sensible way that you could put this together and say that the average color, right, the mean color or the median color? Would you agree there's no sensible way of doing that? Because why should blue be first and red be second and green be third? That just happened to be the way I did my table. You can't line up the colours and walk to the middle and see what colours there, because the colours have no particular order to them. You see that what measure of centre you get is highly dependent on what kind of data you've got to do it to. Right? So things that are just nominal data, the mode is the only measure that makes sense. Now, if you move up the food chain to ages of people and weights of people and things like that, you see that the mean and the median are very useful measures, whereas the mode isn't that helpful, right? In a lot of cases, it's not that good. Right. Suppose I have two people that play golf. And the mean of the first guy is 75, and the mean of the second guy is 80. So you play, I don't know if you've ever played golf, you know, you hit that little white ball around 18 holes and you add up how many shots you took. And this guy on average takes 75. That does not mean, agree, that doesn't mean that every single game of golf he's played in his life, he took 75 shots. Didn't he sometimes have a good week and he played a whole round of golf and he took 70 shots? And then 2 weeks later, he had a really bad day and it was 82 shots and so on. But the average came out, right? In this case, the average I'm using is the mean of 75. And his friend plays and he's got a mean of 80. Based on this data, if these two people had a game of golf, who's most likely to win? Oh, by the way, in golf, you win if you do fewer shots, in case you don't know a lot about golf, right? Who's going to win if they two had a game against each other? It's not a trick question, but audience participation's good.
The first fellow.
Yes, thank you. Right? Not a trick question, right? Now, do you see that in this case, the mean was a way that you could make that decision? If all I showed you instead of these two numbers, right, these two summaries, was I showed you the last 200 games that this guy played as a big list of numbers on a couple of pieces of paper, and then the same thing with this guy, and I handed you the bits of paper and said, these two guys are going to play each other, who's likely to win? Wouldn't you look at it and say, I don't know how to tell? You see how raw data that's not summarized makes it very difficult to make comparisons between two groups of data, right? Whereas a single number, in this case a measure is centered here, could do that. Couldn't I also tell you what the median of those two golfers are and you could make the same kind of decision? You know, the guy who had the smaller median is probably going to win. And what was qualify this probably? Couldn't this guy have a great game and maybe do 73? And this guy could have a horrible game and do 77, and so he could lose. But in general, wouldn't you agree that this guy's probably going to win more often than he loses? Now, if you were doing gambling, which you probably shouldn't, but if you were doing gambling, can you imagine that the people who put the odds on who's going to win a particular golf match, right? So, you know, golfer A is playing, professional golfer A is playing professional golfer B, and you know, this is the final, 1-on-1, 18 holes, somebody's going to win. You put money on which one's going to win. Do you see what they might be looking at here? The people who are interested in that, wouldn't they be looking at the average number that these golfers took to typically complete 18 holes? And the golfer that's likely to win, doesn't he get smaller odds? So this guy may get 2-1, and this guy will get 1-2, you know? If you know anything about odds, that's basically saying he's twice as much chance of winning as the other guy has. Cool. Is there any other questions or anything I've gone over that you'd like me to maybe say a little bit more to? Well, what I'm going to do now is we're going to go in and we're going to have a look at the homework. If I can find it where I done put the thing. Did I set this up? Probably not, knowing me. I'll take it back. I did. So we're looking at section chapter 3.1 right now. And so if I hit this fella, you probably won't see this yet. Okay, we're good. And then I'll go out and in. We'll go over some of the questions and just get you used to the way the homework works. So there's 11 questions allegedly in this. I think there's more than this. Okay. They start off with, consider the mode, the median, and the mean. Which average represents the middle value of the data?
Why, that'd be the median.
I would agree. Which average represents the most frequent?
The mode.
Yeah. Don't you like it when questions are so simple as this? Now, not being a genius here, but have done the job a lot, would you agree that there's a very good chance that the third one's going to be the mean? And it is. So, can you remember the mu and the x bar that I talked about at the beginning of today? This is where this question comes in. We call the data x bar, and it's called a statistic, and the parameter is called mu. Statistic is the name we give when we get the data from the sample, and we call it a parameter when we get the data from the population, so it would be that one. Oh, I didn't know this question, or I didn't recognize this one. In question 3, when a distribution is mound-shaped symmetrical, I don't even know why they stick this word mound-shaped, because it's idiosyncratic to this textbook. Symmetric's good enough, or unimodal symmetric would probably be a nicer way of saying it, right? You got one hill. What is the general relationship among the mean, the median, and the mode? Is the mean less than it, the mode, and the median? Is the mean greater than it? The median and the mean are approximately equal, or the mean and median and the mode are approximately equal? So I guess we've got a choice here, so I'm picking that one. Right. And then you get a whole load of very small data sets and you find what the mode, the mean, and the median is. If there's only 5 numbers, I don't think it's probably worthwhile you doing the calculator. Can't you do those kind of ones in your head? I mean, right. So it wouldn't be too hard to add these up and divide by 5, because that would be the mean. Would you agree that the middle number, because they're in order, would be what, the 4? So that would go there. Let's see if I can add these up. 5, 10, 15, 19. 19 divided by 5 is almost like 20 divided by 5, and take off a 0.25, so it's 4.75. And the mode is the most popular answer. So, yeah, that kind of thing. Now, this here is a little bit vaguer. if the numbers that you're using, right, in this case, can you pretend it's these numbers here? If the numbers that are using represent codes, and it's codes for colors. So the 1 is red t-shirts, right? And 2 is blue t-shirts, right? And 5 is green t-shirts, some code like that, right? If that was the case, which measure of average would be the most sensible to apply to the data? So if those numbers were really just codes for red, blue, and green, would you use mode, median, or mean? Which one of those 3 would be the most sensible to use?
You'd use the mode.
Yeah. But if the data represented, you know, the number of children in the family, or the heights of something, or the weights of something, couldn't you certainly use the mean or the median, right? Especially. And that's essentially what's going on here. And there's another simpler type of question. And I'm going to leave this for a minute because there's some questions there that I can now talk to. Suppose I have got some data and I'm going to make my data very easy to calculate. 1, 2, 3, 5. So that's 5, 6, 10, 4, and 8. Right. Now the mean of this data is 3, 7, 12, 20, is 4. Good. Suppose I add 7 to all the numbers. So instead of that being 1, it's now 8. And that guy is 9. And that guy's 11. And that guy's 12. And that guy's 15, right? That's what I've done. If I calculated the mean of that, I know what the answer is. And I didn't do it in my head. I used a logical argument for why the mean would be 11. If you add 7 to everybody, does it make sense that the mean would also increase by that same amount, 7? Agreed? Now, suppose you double all the numbers. This time, I'm not even going to write it down. 2, 4, 8, 10, and 16. Suppose I doubled all the numbers in my data set without even doing a calculation. It's reasonably easy to make a prediction. What do you think the new mean is going to be of the doubled data?
8.
8. And can you imagine that all this data here was inches? Right? And they decided to multiply them by 2.54. It seems a reasonably weird number to multiply things by. Wouldn't the new mean just be 4 times 2.54? And that's something I'm going to do on the calculator. And the answer is 10.16. Oh, does anyone know why I chose 2.54?
Centimeters.
Yeah, I'm converting it. Have you noticed that sometimes you have data that's in inches, but that's because Americans like inches. But you know, if you're going to publish anything in a scientific paper, if you're a true scientist, don't you have to work in centimeters and meters and all that good stuff? So you may well have to go and convert the data into that format. So I would expect, I don't teach chemistry and physics, but do you work for the most part on the metric system when you do stuff?
Oh yeah.
Okay, yeah. Can you see why you need to? Because if you start publishing papers and a German or a French scientist in the same field looks at it, he's going to wonder what these numbers are, because they probably don't even know how big an inch is. I mean, that was like 80 years ago that they even thought about using things like that. So But you know the conversion is easy, isn't it? You can just take your data and do a very quick change on it. So you could plug your data into a piece of software and say, here, this is my raw data. Can you turn them into centimeters? Because I'm going to publish it, and some French guy's not going to know what the heck, what these numbers are, because they're in the wrong units as far as their life's concerned. Do you still use Fahrenheit in chemistry?
Never in chemistry, no.
Thank goodness. You should use centigrade, degrees, or Kelvin, even better. Do you use centigrade, degrees, Celsius, centigrade? Two names for the same thing? Yeah?
Yeah, ideally.
Yeah. Do you use Kelvin? Do you know what that is? Right. So you got your data in Fahrenheit. It's probably not a good idea to publish a paper, because if it's going to go international, the French are going to look at it and say, I don't know what these numbers are. What's this? I know that you use Fahrenheit, but I don't, it's hard for us to compare. So we need to be able to do that. So what's the bottom line here is, if you take data and you double it, don't you double the mean? If you take data and you add 10 to it, don't you just add 10 to the mean? Right. Do you think that's going to be true if I take the same data and found the median? Right. So in this data set here, the median is the middle number, which by hook or by crook ended up being the same as that number, but it doesn't matter, right? Isn't the median 4? If you add 7 to everybody, do you see that the median is 11? And if you doubled everybody, can you trust me, the median would be 8. So if you do the mean or you do the median and you do basic calculations to all the data, and by basic calculations, I just mean you add the same number to all of them, or you subtract the same number from all of them, or you double all the numbers. So you multiply them all by 2.54. Doesn't the same thing happen to the mean and to the median? Whatever you did to the data, the same thing's going to happen to your measures of center. Now, it doesn't really work on this data set. What's the most popular number in this data set? 3, right? So the mode is 3. If I added 7 to all those numbers, wouldn't the mode change to 10? If I doubled all these numbers, wouldn't the mode change to a 6? So every single measure of center has the same property, that if you do a basic calculation to them, the same thing happens to the measure of center. That's pretty resilient of it, right? So it allows us to do calculations. And so if I, excuse me, if I went back to the homework questions, there was a couple of questions there that went something like, here is a set of data. Suppose you added 8 to all the numbers, what would the new mean be? Or suppose I doubled all the numbers, what would the new median be? And basically, can't you just use your answer to the earlier part? The mean used to be 7. If you doubled all the numbers, the mean is now going to be 14, right? So you don't actually need to physically do the question from scratch, doubling all the numbers in your calculator and then going in and finding the answer, right? You can get it in a much quicker way than that. Any questions about that, Awikal? Well, that's 3-1 done, as much as I feel I need to cover. So we're going to move on to 3-2, which are measures of spread. Now, if measures of center tell you the guy that's typically in the middle, this new thing, this measure of spread, is a statistic that tells you how spread out the data is. Huh. So what am I getting at? Let's do some numbers, some data. Here is a set of data, and we are going to find a statistic that measures how spread out the data is. There were 3 measures of center, right? In no particular order: mean, mode, and median, right? All start with the letter M. Mean, mode, median. There are 3 measures of spread. They are called the range, in no particular order, the IQR, which is what everybody calls it, but its real full name is the interquartile range, and 3, typically, at least this textbook uses S, but in a lot of other textbooks they call it ST, but it's just short for a thing called the standard deviation. Have any of you had to calculate the standard deviation because you did some experiment and you did measure the temperature 20 times? So I'm getting some nods here. Wasn't it a horrendous calculation? Did you do it by hand and you did what's called the deviations and you squared them and you added them up, or and then you divided by 1 less than the number and then you took the square root of the whole mess? Is that how you did it? Or did you plug it into your calculator and you hit some buttons and the answer popped out? Right. We're going to plug it into the calculator and some numbers pop out, right? Some of the questions in this section, I'm not quite sure of the phrasing, but the question says, do it by hand, or sometimes they give you the choice and they say, do it by hand or use a calculator. Whatever way they phrase it, well, you just always do it by the calculator, right? Okay, if you go and you want to do it by hand, feel free, but all that is busy work. It takes forever in a day, and you're still just going to simply get the calculation. If you want to know how you would do it, by all means do so, because some people don't like magic. They want to know, where does this number come from? Well, you can go and look at the textbook and they'll talk you through an entire calculation, right from start to finish, and you can see what it's like. But for our benefit, we're just going to calculate the thing using our calculator. So we're going to get this number that measures spread. So a big number means that the data is really spread out, and a little number means that it's not so spread out. So how do you get the range? You take the largest number and you subtract from it the smallest. In this case, 20, take away 1, the answer is 19. A little bit circle around that. There's not an awful lot of advantage to this measure of spread, except that it's really quick, right? Because all you need to know is who's the biggest, who's the smallest, subtract them. Let me ask a question about outliers. If your data has an extremely big outlier, or for that matter, an extremely small outlier, won't the range be heavily affected by it? Suppose that 20 wasn't 20, suppose that 20 was 200. Wouldn't the range now be 199? Can you see how one number, and it's only one number out of 10 or 12 numbers, or it could even just be one number out of 200 numbers, but one outlier will totally inflate that and make it hard to really judge how spread out the real data is. Could almost all the data be very similar to each other, and then one crazy number miles away? But that range would say, oh, the range is huge. That must mean the data is all spread out. No, the data is really close together. That outlier just makes you think it's spread out. Now, the interquartile range, I'm going to show it by hand, but we really do that by calculator as well. So here goes. I think I've got enough room up here to do it. I have 11 numbers here. Hopefully you can see the darn things. I don't know if that helps, probably doesn't, but anyway, can you see the numbers a little bit clearer if I get closer? Now, is there going to be two numbers in the middle, or is there just going to be one number in the middle, which is the median? What are you going to get when there's an odd number like this, 11 numbers?
One in the middle.
Okay, and isn't it going to be, strangely enough, guy number 6? So here goes, 1, 2, 3, 4, 5, 6. And just to make sure, 1, 2, 3, 4, 5, 6. You see it's the same guy both sides. This fella here is called the median. Now, how do you get the interquartile range? Well, you get a guy called Q3 and you subtract from it a guy called Q1. They're called the third quartile and this guy is called the first quartile. Well, do you see that median that I just got? Can you imagine that there's a wall there, right on top of it? Do you see that I've now split my data into two equal halves? Do you know the middle of this is called Q1 and the middle of this is called Q3? So in this case, I kind of deliberately made it nice for myself. Can you see that the guy that's going to be Q1 is this fella? Can you see he's in the middle? Who's going to be the middle one on the big side? I agree, I saw your lips move, so 15 it is. So to get the interquartile range, you take this guy who was 15, Q3, and you subtract this guy who's 10, and you get the answer, 13. Now, if you're going to get the standard deviation, you add them up and you get the mean. You subtract each of these numbers from that mean, and that gets you a thing called the deviation. You then square all those numbers. That gets you a guy called deviation squared. You then add up all those deviations squared. You then divide, not by 11, but n minus 1. You divide by 1 less than that, 10. And then you take the square root. That's why you use calculators, right? So let's get the calculator to do that. And I'll show you in a few moments, hopefully, how to make that happen. That's not the one. Can you see the calculator? Oh, okay, it is right. So I'm going to put it on. Let's just clear that screen for a minute. Hit start and go edit. Oh, you can imagine what's going to happen. Aren't you going to have some numbers from a previous question in the way? I guess you could do is you could move over to L2 and then do the numbers there. Me personally, let's assume I don't need these numbers anymore, right? I got the answer, it was right, I'm fine. Just keep hitting delete a lot until they go away. There is another way of doing it, but I don't want to show you because some people hit delete and they destroy L1 and now they've only got L2 and it causes a whole load of hassle. But if you know how to do it, that's fine, but I won't mention it in case I cause more damage than help you. So the data's going in right now, so it's going to be 1, 2 2s, a 3, a 5, a 7, a 9, an 11, a 15, a 16 and a 20. Now, I'm pointing at the screen, you can't see me pointing. L111 is 20. That's telling me that I'm about to type in the 11th number. Wasn't there 11 numbers in my data set? Always have a quick look at that, because imagine you're doing 25 numbers. If you get to the last number and it says you've only got 24, doesn't that mean you've missed one? And you're going to have to figure out who it is. It's probably kind of hard to figure out who it is, but at least you know you're wrong, because if you don't, you're going to come up with an answer that's not right, right? You're going to be missing a value. So I'm good, enter. Now I'm going to hit start. I'm going to go to calc again. I'm going to go one variable statistic, just like we did before in L1, and I'm going to hit enter. Now, do you see that the mean of this data is 8.27? And if I scroll down, or not so much scroll down, but do you see this guy here that is an S and then an X next to it? See this guy here? That is the standard deviation. In this particular case, the standard deviation is roughly 6.5. So the guy that is called S little x is your standard deviation of your sample. The guy next to it that looks like a funny zero with a little bit added on, that's called sigma. That is a standard deviation of the population. So if you ever get a question and they say, there's only 20 people in the world that are, whatever it is, this blood group, whatever. That's a population. If you find the standard deviation of a population, you're going to use this 6.1 guy, right? Most of the time, your data is a sample, right? It's a small subsection of the entire population. So most of the time, you're going to be using that top one. And that is kind of how you do it. So that's pretty quick. Agreed? If you let the calculator take the strain. I'm just curious, those people who've done standard deviation, did you do it that way? Did you do it on a T84 the way I just showed you? Right. So, I mean, you're going to breeze through some of these questions, are you? Because it's some you've done in other places, so you're hopefully going to not have too much of a problem. And for those who are new to it, of course, that's going to take you just a little bit more time. So we've got this Q1, we've got this Q3. I subtracted them to get 13. I wish I'd got my data here. Hold on, I can. If you just bear with me for a second, I'll go back to my calculator and I'll show you that I could even get the answer by just scrolling down. Can you see Q1 is 2? Can you see Q3 is 15? Subtract Q3, take away Q1. Can you see the answer that I got earlier was 13? Yeah. So you can actually get the interquartile range. You can get the standard deviation. In fact, now that I'm looking at it, couldn't you get the range? Do you see that in this page here, the smallest number is 1 and the biggest number is 20? Won't the range just be 19? So if you put in a big set of data, especially data that's all jumbled up, isn't this going to save you a great deal of work, a great deal of time? Because if that data was all jumbled up and I said, I need you to find the median, isn't your first job going to be to rewrite the numbers in order? Can you imagine there's 25 numbers and you have to rewrite them in a list from smallest to biggest? Just how much awkwardness that could cause you. So calculators are great things. Now I can move back a little bit. Any questions? Are we good? Are you comfortable about these 3 measurements? How you calculate them? Thumbs up, perfect. So I'm going to talk about very similar kinds of things that I did for the first group. Let's look at what do outliers do. We've kind of touched on it. Right, so we have range. We have IQR, interquartile range. And we have standard deviation. See if this last number was 200, not 20, but was an outlier. It was 200. Would the interquartile range be changed at all? Wouldn't Q1 still be 2? Wouldn't Q3 still be 15? That number turning into 2 million or 200 or 200,000 has no effect. So interquartile range has no effect. Does an outlier affect the value of the range? Well, can you imagine right now, isn't the range 19? But if I made this an outlier, if I made this 200, wouldn't the range become 199? And it is affected. In fact, it's affected badly, right? It's not just affected a little bit, isn't affected a lot, right? And 19 turns into 199. It's pretty bad, right? It's a pretty bad effect. One number can do so much damage. You might not know this because it's kind of hard to tell how you calculate the standard deviation unless you do it by hand. So this one you're going to trust me. Do you know that the standard deviation also gets affected badly? If you put in one really big outlier or one really small outlier, the effect is that the standard deviation is much bigger than it would have been if that number hadn't been there. So something that might have a standard deviation is 6.5, which it has right now. I'm going to go back to that data set and I'm going to change that 20 to 200, right? That's the only thing I'm going to do. Do you think that number there might become, I don't know, 10? Do you think it might become 40? I mean, how much does it get affected? It's kind of hard to judge, isn't it? So let's find out. I'm just going to do it because I don't know myself. I could have a guess. It's probably going to double it, and that's just a guess. I'm going to find out by trying it out. I'm assuming that you can see that. Can you see the calculator? Okay, so put on the power, put on stats, go to edit, just zoom down to the last number, right over the top of it, it's now 200. I'm going to go in and collect the data. Whoa. Wasn't even close. $58. A standard deviation without that outlier was just a kind of normal kind of value, 6.5. You stuck in one huge outlier and it's 58.4. Now, when I gave you my guess, it was truly a guess. It's very hard to judge, isn't it? The effect of one number on a standard deviation. If this data was bigger, so can you imagine there was 100 numbers in it instead of 11? That 200, that outlier, would have a less significant effect. In other words, if you've got a really big data set, right, a huge data set of thousands and thousands upon people, one really big number, as long as it's not a Bill Gates kind of outlier, right, just an extra big number, won't be too dangerous, right, because it kind of gets leveled off a little bit, right? It kind of gets shared amongst the 200 or the 2000, right? And so it doesn't contribute so much. But if it's part of a very small data set, isn't it even more significant? It causes a lot more damage. So outliers are bad. They do affect things badly. So here's an interesting little puzzle. Is anybody here a basketball fan that likes basketball? Because I'm going to pick your brains in a minute if you have. That was the same in the other. What's wrong with basketball? Nobody like it. Okay. I'm going to invent it then. I'm going to have two players. Player A and player B. And the only thing I'm going to tell you about these two players are two of their statistics. First thing, I'm going to tell you what their mean is. Their mean is 30. So in a typical game, this guy, if you let him play for the whole game, will score 30 points. Now, I don't know if that makes him a good player, an average player, phenomenal player, but 30 points is what he's getting. The reason I was going to pick your brain is I would then say to you, can you tell me what a good player would typically score in a basketball game? And that way I could make this realistic, right? So we're just all going to believe it's 30, right? And then I'm going to tell you the standard deviation, but I could also tell you the median and interquartile range, right? But I'm going to tell you the standard deviation. And the standard deviation here is 5, and the standard deviation here is 20. Now, in one respect, aren't both these players equally good? They both, on average, score 30 points a game, right? But the standard deviation is significantly different. So if I was going to describe these two players, what I might say is that if you looked at player A and you looked at all the games that he played, and it was symmetric, we'll assume that it is, his data might look something like this. And he might score anywhere from 20 to 40, roughly, right? Because when it's an average, that doesn't mean every single game he plays, he gets 30 points and exactly 30 points. Doesn't that mean some games he has a good game and he scores 40? Some days he has a bad game and he scores 24, right? Things like that happen. All the 30 means that it's a typical number in the middle. Now, if you look at this guy who's 20, although the middle is 30, doesn't this standard deviation of 20 in many ways kind of means that he's much more inconsistent? Wouldn't this be the kind of player that sometimes he plays and you only get 10 points out of him, and then the next game he plays, he scores 50 points for you? In English, wouldn't we say that player A is a very consistent player? Right? If you go and watch him play, aren't you probably going to see him score around about 30 points, give or take 5 or 10, right? If you went to see this guy play, aren't you going to see sometimes you're going to say, why on earth is he even playing for my team? He keeps missing. And then you go to him the next week and you think, why didn't he play like that, last week? He won the game for us. Now, if you are a manager in charge of a team, statistics is, you may not know this, but there's a lot of people who devote themselves to, in very big clubs, to being the guy who collects statistics on the players. In baseball, they can tell you all sorts of things like batting something average. I don't know baseball, but those there's tons and tons of data. I'm sure there's tons and tons of data about American football players, right? What's the fastest he runs? How many yards on average does that guy get when you give him the ball, right? How many times do you catch the ball when it's thrown to you? All those kind of statistics. They collect those statistics and they find things like the mean number and the standard deviation, because won't those numbers tell you who is a good and consistent player against a good but inconsistent player, right? So here's a question for you. Suppose you're about to play in the final game. And in the final game, you're about to play a team that you've played lots of times before, and they typically beat you by about 10 points. Right? You've won a few games, but most of the time they beat you, 5 or 10 points worth. And you've got a decision to make who to play. Who do you play? Do you put player A in, or do you put player B in? Based on the fact that you typically lose against this other team by about 10 points. Who do you put in?
Wouldn't you put in player B and kind of risk it to try and get more points?
That's what I would do. You see, there's a kind of logic to that. It's a gamble. Because he might bomb it, but see if he bombs it, don't you get beat? But weren't you probably going to get beat anyway? By 10 points. So there's nothing to lose. So you would play Mr. Inconsistent. Now here's another one. Suppose you're in the cup final against the team, right? And you've played them lots of times, but you're pretty comfortable about playing them because you typically beat them by about 10 points most of the time. Aren't you going to play Mr. Consistent this time? Why risk it? So can you see that in certain circumstances, player A or player B might be the right choice? But how do you make that choice? I guess you could do it intuitively, but isn't it much more useful if you've got numbers to back up your choice? And so we look at that and we use standard deviation as a way of looking at how consistent someone is. Here's another example. Suppose you're in a factory that packages potatoes. You get big bags of potatoes, 30-pound bags, right? Big heavy bags of potatoes. And you've got this machine that basically does it for you, right? Most things are automated. And you can buy two machines. You can buy machine A or machine B, and they're both designed to produce 30-pound bags of potatoes, right? That then get shipped to wherever, the warehouses, supermarkets. And you've done a sample from each machine, right? You've got a little test run, you went to wherever it was, and you looked at the two machines. And this first machine, 30 pounds is the average, which is what you want, right? Standard deviation is £5. And this second one, standard deviation is £0.5 pound. Which machine would you think would be the best machine to use for packaging your potatoes? If you then are going to sell them on to the supermarkets and whatever.
Machine B.
Agreed. Why?
Because it has less air in the weight.
Yeah. So when you buy, when you go to the supermarket, don't you want to grab, if you grab a 30-pound, God, that'd be a sack, right? You grab a 30-pound sack of potatoes. Don't you want it to weigh, not on average 30 pounds, don't you want it to weigh 30 pounds, give or take a couple of potatoes, because nothing's perfect. If you got this machine, couldn't you sometimes be getting a 20-pound bag of potatoes and the next day you could be getting a 40-pound bag of potatoes? Isn't it basically all over the place? Consistency is not good. When they do very, very precise machines, you'll find that they use a word called tolerance. Have you ever heard that term, tolerance? Right, so I am going to do a nut and a bolt, and that tolerance is going to be plus or minus 0.01 millimeters. Can you imagine what you're making there is a nut and bolt that are so finely tuned that they're almost perfect matches of each other, right? If the tolerance is plus or minus 0.1, do you see that you might get a couple of shaky ones that, okay, they fit, but they're a little bit wobbly, right? When you're building certain things, the tolerance doesn't need to be that good, right? You can get away with quite high tolerance. You know, the screw will still, the nut and bolt will still fit. But if you're putting something in a spaceship and somebody's life depends on it, do you want even one loose nut and bolt? And that very often that's what kills people, just one loose nut or bolt in the wrong place. So when they do spaceships and anything that are very expensive, like aircraft, do you know that the tolerance on most of those things is extremely tight? Tolerance is actually just standard deviation. Small standard deviations is a measure of the tolerance, right? And when NASA buy nuts and bolts that they use, I don't know if they use nuts and bolts, but whatever it is, screws, whatever they use, do you know that they will spend a lot more money to get really good tolerance on the things that they buy? Because they know every single thing on a space station needs to be bolted down really well. You don't want little things floating around because they listen. So that would be another example. Hopefully I've argued why standard deviation is a useful thing. Let's show you a guy called Box and Whiskers. I believe it's also called a box plot, but I don't like box plot. I think Box and Whiskers is a nicer name. And it's a diagram that uses what's called the 5-figure summary. Check my time here. The 5-figure summary is the minimum, Q1, Q2, which, by the way, Q2 is just another name for the median, just in case you look at a textbook and you see it's called Q2. Q2 is the median, and Q3, and then the maximum. So can you imagine we had a big set of data? I'm not going to do this one, but imagine we had a big set of data. In fact, I'm going to use, although you can't see it, I'm going to use the data from an earlier question. The minimum was 1. That was 2, this was 7, that was 15, and this was 20, right? Remember that set of data we had earlier? This is called the 5-figure summary. On your calculator, these are the last 5 numbers that you'll see on your screen. So they're all there together in the order that you want. And this is going to create a Box and Whiskers diagram. So the way you create one is you draw a nice straight line, which that isn't. And the smallest is 1 and the biggest is 20. So I would go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? Basically a scale, right? Horizontal scale. And I need a story for this. So let's say this is the ages of people. Right? Just off get heading. Now, the minimum is 1. So you do a little mark at 1. Q1 is 2, so you do a long mark at 2. The median, sometimes called Q2, is at 7, so you do another long mark at 7. Q3 is 15, you do a long mark at 15. And the maximum is 20, you do that. And you join these 3 guys together, like that. And you join these 2 guys together, like that. Have you ever seen a diagram that looks like that before? Michaela, I noticed you nodding your head. You want to share? Where have you seen that kind of data before, that kind of picture?
If you go on Canvas and look at the grades, you can see a Box and Whiskers plot of, if the professor allows it, you can see a Box and Whiskers plot of all the grades for that particular assignment.
So you can get an idea from this picture, can't you then, what the kind of, actually, can I change that then? Because I like your story better. These are the scores that students got in a test, right? Now, when I look at this test, can you see that somebody got 20 out of 20? At least one person. And can you see that some poor soul didn't know what he was doing and got 1? Can you see that this must have been quite a hard test because the typical guy in the middle only gets 7 out of 20? And can you see this middle box, which is essentially the middle 50% of the people? Can you see the basic shape of it, right? We call this a box and whiskers or a box plot. And what it does is it takes the 5-figure summary and it creates a very interesting picture of it. It's a very relatively simple picture to make. Would you agree that if you've got these numbers, it's not that difficult to do that? The things that some people make a mistake in doing is, well, you make sure that this is an even scale. Don't just go 2, 5, 15, 20 and make them all the same size, right? Everything should be spread out accordingly. In this particular situation then, imagine that I did 2 of them, right? And so I collected some data and I got a box plot, right? One of these box and whiskers fellas, and it looks like, say that guy here. And then I got another box plot, and it looked like that. And this is class A, and this was my other class B, right? And I guess you need numbers, but I'm trying to do this as a visual thing. When you look at the 2 box plots for these data, can you imagine they're sharing the same scale? Can you see that the typical score in the middle was still 7? Let's say that was 7. Do you notice that this box is bigger than this box? The distance from the top to the bottom, right, from side to side, that number from there to there is the interquartile range. So if the interquartile range was 7, that would be 7 boxes long. Right, if the interquartile range was 3, that would be 3 boxes long. So do you see that the interquartile range is actually a measurement of the distance from Q1 to Q3, which in this picture is a measurement of how big that box is, how wide that box is. So that's a kind of nice connection. If I was looking at these 2 groups, would you agree that class A, the grades are much more spread out than class B? Right, there's much more variation in the marks. So you can tell that by, looking at the 2 ends. You see they're much further apart. In fact, looking at the size of that box, isn't that box much bigger? Well, bigger, maybe not much bigger than this one. So that's one thing you can get from a box and whiskers. I'm going to show you 3 pictures of 3 different kinds of box and whiskers. I'll call them number 1, number 2, and number 3. So you collected 3 sets of data and this is what you got from them, right? Which one of these 3 would it be fair to assume is probably symmetric in shape?
Number 1.
Agreed, you're correct. Want to share why? What made you decide that?
Because the majority of the data is in the middle.
Okay, and it's equally split. Agreed? And would you agree that the tails are roughly, you're allowed a little wiggle room, that one looks a little bit longer, but pretty much the same. So if you get a box plot that looks like it's been cut in half and the 2 boxes, are equal, it's been cut in half and the 2 tails are roughly equal, then you are looking very likely at symmetric data. In other words, it would look like that, right? Okay, one of these is skewed left and one of these is skewed right. What's number 2? Skewed left or skewed right?
Skewed left.
after a long pause on the word left. Agreed? Okay, since you've got it, share it with us why you decided that, because you're correct.
Because I had a 50-50 chance one way or another.
Oh no, that's a wrong answer.
No. It's the data is clumped over there on the right side, and it's therefore going to be skewed the opposite direction of what it is.
Oh, so you look at this and then decide that that works. My brain looks at it the other way. Do you see a long tail in a long box? So it's skewed left.
Mm-hmm.
Right. So box, skewed left. Pretty obvious then, skewed right. Wait, if it ain't one, if you reverse the pattern, you're looking at a skewed right. So if you looked at this data and you looked at it in its entirety and you did, when I do these, do you know I'm pretending I'm doing histograms? Yeah, little rectangles, but we just do it as curves for quickness. So if I was doing this one, wouldn't the data probably look something like this? And if I was doing this one, wouldn't the data look something like that? So far, so good? Right. Now, we've only got a few more minutes left in this, so I want to spend what time that we've got returning back to a guy called Outliers. Oh, darn it. I'm getting old. Let's try that again. I've got some data and I've got a candidate to be an outlier. Maybe he is, maybe he isn't, right? Now you can look at the number and you can sometimes you can argue, and sometimes it'll work, that 25 is significantly different from the rest of the data, which it totally is. I completely agree with you. But if that 25 was, imagine it's the same data, but let's suppose the last number wasn't 25. Suppose it was 17. Is it an outlier? It's a little bit harder to, justify that. If it was the same data and the last number was 13, I think almost everybody would say 13's not an outlier. 11 to 13, hey, they're almost on top of each other. Isn't there a grey area between definitely not and probably definitely is? So we need a test. We need a way of deciding, like a yardstick that you measure against it. And if you're bigger than the piece, the yardstick, you're an outlier, that kind of analogy. And this is going to be the one that the textbook uses. You're going to get the mean and you're going to add 2.5 standard deviations. And you're going to get the mean and you're going to take away 2.5 standard deviations. If you are bigger than this guy, you're an outlier. If you're smaller than this guy, you are an outlier. So I've got a very short set of data here. I'm just going to do it in my calculator because it's probably quicker than going out and in. So if you can bear with me for a few minutes, I will do that. 1, 3, 5, 7, 7, 9, 11, and finally 25. And although you can't see me doing it, I'm now doing all the other buttons that I need to press. And you're just going to trust me on this, that the standard deviation in this case, right, in this set of data here, the standard deviation ended up being 7.4. And the mean of this data actually is 8.5. So you take the mean, which is 8.5, and you add two lots of the standard deviation, and I have just discovered something. That guy doesn't count as an outlier. Let's see why. 8.4 add 2.5 times 7.4, which is 18.5. And you add them together, you get 27. So for argument's sake, can I pretend he was 28? Just so I can get away with this, right? Would you agree now he's an outlier? If you're bigger than that number, you're an outlier. So won't 30 and 33 also be outliers if that was the last number? So the mean plus 2.5 standard deviations gives you the upper value. As long as you stay inside that number, you're okay. Even if you're big, like 25 was really big, but 28 was too big, right? Now you're an outlier. I don't have a small number, but if I wanted to do a small number in this case, do you see I would do 2.5 times the standard deviation, but I would subtract that number. I believe if I do that, you get the answer -10. So this data would have to be temperatures. So if you found a piece of data over here and it was -20, wouldn't -20 then be counted as an outlier? Okay. So let's make up a story. I've got some data and the average height of people in Scotland is 63 inches, right? We're quite small people. And the standard deviation is 4. Would a person who's 69 inches tall be considered an outlier, an exceptionally tall person? Well, let's find out. X bar plus 2.5 standard deviations. 63 plus 2.5 times 4. 63 times 10. And the answer is 73 inches. And the answer is, he is not an outlier. He's tall. Wouldn't you have to be over 7 foot, in fact, over 7 foot 1 inch, to be considered an outlier? So do you see that we've now got, we don't do any guessing. There is a calculation that you do, and you get a number out of that calculation, and you have to be bigger than this number before you're an outlier. So you might look at the data and you think, oh, 70 inches is a really big guy, right? Yes, but he's not an outlier. But a 75-inch guy or a 79-inch guy, they are really big and they are an outlier. Do you see, we now have a non-subjective way, right? Because before that, you kind of looked at it and some of you would say, yeah, 25, like I did, 25 is an outlier because it's pretty big. And did you see I actually get caught out because 25 wasn't an outlier? Right? You had to be bigger than 27 before you were an outlier. But you see, that means now everybody agrees what an outlier is. So that when you're doing, remember those things that we talked about, we don't like that number, he's an outlier, I'm going to throw him away and then recalculate my question without him. Remember we had to do that sometimes? Do you know what you have to do now is you have to prove that he's an outlier before you can get rid of him. So you calculate the data, the mean, and you calculate the standard deviation, and you figure out this number. And was your guy, you know, remember the 200 or something that we got? Yeah, definitely an outlier. Now I can convince the scientific community why I decided that that number wasn't a good one to use in my data, right? But suppose I did it and I got this number and the guy I wanted to get rid of was 25. Remember the one that used to be here was 25. Do you know I have no good scientific background to do that? In fact, I shouldn't be allowed to. And in fact, if you publish your data honestly, you tell people the numbers that you've omitted, right? I've decided that this fellow is an outlier and I'm not going to use them in my analysis, right? This 28 was an outlier. If I put in I'm not using 25 because I just didn't like it because I thought it was too big. You see, that's not very scientific. But now we have got something another person can do. Yep, I agree with you. Everybody in the scientific world says he's an outlier. You're